This month, we're going to be kind of focusing on leveraging spherical tipped tools, circle segment tools, and barrel cutters, basically. Things we're going to cover in the hour that we have. We're going to go over just a brief tech overview of what these circle segment tools can be used for. Optimizing surface finishes being the biggest thing, and then cutting cycle times down, of course. And then we'll go over the tool types that you can use, of course, and then creating those tools within PowerMill. Sometimes there can be some tricks to creating these tools, some information that everybody should know while we go through them. We, of course, have a macro that helps create these tools into form tools if needed. So we'll go over the macro that we have created for that. And we can make these macros that we have during our webinars available to users based upon request. For right now, we are working on a platform that we can use to be able to download those directly from that information or resources page. We'll also go in and touch base on how to set your optimal angle of engagement for these tools. Now, if you look at the picture over on the left-hand side here, you can kind of see what I'm talking about by optimal angle. So the angle of engagement that will be contacting the surface that we want to cut with on that tool, similar to like a ball nose end mill, but if you look at that picture, you can see with the angle of engagement that's set there, your scallop height's going to be far smaller, and then at the distance between your scallop height is going to be smaller, as well as the surface finish created by that, and therefore less optimal for a step down. So you can increase your step down or step over based on the cutter, and therefore increase cycle time and also surface finish depending. We also have a macro that does that within PowerMill. This is something that PowerMill's done for quite a while. I want to say, I remember this back in 2007 or so. I mean, we were able to do and utilize some of these tools within the aerospace industry. Now, over the decade or so, these tools are becoming more and more available, which also means that the price has come down quite a bit. And we're getting to a point where most cutting tool manufacturers actually supply these tools. After that, we'll just go over a few of the tool paths that are mainly supported, mostly due to the macro, and then go over again the angle of engagement with that. Just to kind of cover the basics of the tools that we're looking at covering today. So these are the typical profiles that you'll see along spherical tipped type tools or barrel tools. Of course, the standard barrel profile being more like an end mill with a bulge in it. And this was kind of one of the first introduced barrel type tools, you could say. Next to it, we've got what they call the drip profile. It's basically still a spherical tipped tool where you have multiple radiuses making up more of a conical shape on the cutter itself. Of course, conical profile having more of a steep angle. And then, of course, lens being kind of the bottom of the tool or the cutting tip of the tool where you'll have a full radius or a larger radius across the cutting portion of the tip. Mostly used for flatter surfaces. They have a picture there that's got it wrapping around a cylinder. All these different tools can help in many different ways for the different types of geometry. But as usual, geometry is king here. And that also means when you're selecting your cutters, you have to keep your geometry in mind, how you're going to reach down into the cut, how much clearance you have on the angle, and of course the surface radius itself, whether or not the radius is going to fit within the profile of the cutting tool. Now, all of the cutting tool manufacturers do have ways, and on their websites they have different things that help with the selection of these tools, and we'll kind of touch base on a few of those things as we go through the demonstration today. I'm going to jump over to a little bit of information. This is just an article that I pulled up. It's a little bit old. It's like from 2019, off of Mold Making Technology. Just kind of with a brief explanation of, what we're looking at for improving the contact of your cutting tool to the surface of your part and improving your tool path. Just some brief overview here of what we're looking at. So typically when we cut surfaces on a ball end mill, and especially if we're coming at this from a 3D standpoint, you'll see you get your contact scallop height, and that's going to determine the surface finish of your cut, as well as the efficiency of your tool path. This article goes over a few of the different types of tools as well. It's a pretty decent article as far as a basic overview goes, and I can make this available to anybody as well upon request. Give you the link, whatever the case might be. Do email us, or you can send it here in questions or chat, and we can make all that information available. But this article is pretty decent, so I thought I'd pull it up just as a reference, so you can get to know the technology just a little bit better. Now, when I think of the efficiency of this, I do like to show kind of an example, and I'm going to pull up one of my calculators here that I like to use, just to kind of show what we're talking about as far as scallop height is concerned. And I'm just going to reset this real quick so that it's on ball end mill, and I'm just going to go ahead and pick like a 1/4 inch ball end mill tool here with 2 flutes. When we're calculating the efficiency of a surface finish, we're usually looking at our scallop height for that. This calculator does a pretty decent job here of allowing us to either use the scallop height depth as a reference or even surface finish in RA to kind of calculate what we would need for a step over across the surface. And if you look at the image here, this gives us kind of a good little distance detail for our step over overview. And I'm just going to go ahead and just enter, say, 50 millionths there. And you can see here that a 1/4 inch ball end mill cutting across a straight flat surface to get that scallop height to maintain that surface finish is going to be about 7 thousandths or so. And usually we'll cut down to about 2 to 5 in the industry. I see quite often, depending on the size of your cutter, just as a basis so that we can be sure to get those surface finishes. Now, these calculators do a decent job, but of course, we've got length of the tool to consider, as well as RPMs, type of material, all the different factors that are still in play here. But to just give a good base example of what we're talking about improving here, these type of spherical tipped tools allow us to increase that contact point for that cutting radius 10, 20 times sometimes. So instead of a 250 thousandths tip radius, we can say maybe even a 4-inch radius diameter for that type of cut. And when we do that and we look at our scallop height, and I do have to reset the calculator here to make that work, what we're looking at is a dramatic increase. So instead of 7 thousandths or 5 thousandths and below, we're now looking at 20 thousandths, 30 thousandths, sometimes 40 and 50 thousandths, depending on the geometry and the cutter. So we're basically quadrupling, if not more, our step over capability with this type of technology within the cutters. Let's jump into PowerMill real quick. I'm going to open up just in a fresh version of PowerMill here. We're going to go ahead and import a few of the cutting tools as we go along here. As I do that, let's go ahead and just take a look at a few of the cutting tool vendors that I may be talking about. I think I'll go back to the slide for this. So just looking at the slide, and now in my experience, I have used the Imugi brand of cutters for this, and also the Iskar brand of cutters. I have yet to use personally the Freesia cutters, but I have programmed for them and sent them out to customers that do like to use Freesia. And this cutting tool brand actually has quite a bit of data on the technology itself and quite a variety of tools. So this is these 3 brands to me are just the ones that I'm going to kind of take a look at individually on the websites real quick, just so you can see. And I'm going to go ahead and head actually back over to the internet here. Let's start out with the Freesia tool, because I did like their tool selection. They basically have a different variety of it where we can come through, and based off of the type of material, they have a full line of the types of cutters. Now, when we're looking at these types of barrel cutters, they do give us kind of a difference in what we're trying to do. Typically, I usually don't do like a semi-finish operation with these types of tools. I'm focusing more on finish and super fine finish when we're trying to get down to mirror finishes on tools or something like that, or in aerospace when I'm trying to finish and get down on thin wall webbed type parts. You can kind of see, well, what type of tool and what kind of contact point are you looking for here for your tool? Now, I like these examples and the pictures that they give, because this kind of shows, are we looking at thin wall with narrow kind of access to the geometry? Are we looking at rigidity? Are we going to be looking more at a bowl type with a little more steep of an angle? And you can kind of pick what you're looking for here. And as you pick it and go through their website, they'll give you the type of tools as a suggestion. And we can actually come in and just select that tool, and then they give us all the relevant data. Now, this is their website. It's pretty decent. I'll go over here to their PDF. They do have a PDF on their cutters as well. That's a white paper that you can look at that does give a little bit of information about the technology behind it as well. So feel free to get in contact with any of your vendors ask information about this, ask for more information on the cutters that they support and what they have. And they can also send this information to you. Now, you will want this information as reference. I had this pulled up to a page, and as we go through the demonstration today, I'm going to show you what information I'm going to have to pull, both to create the cutter as well as to apply the most optimal engagement angle. So you can see in the image that I have from their PDF here, if I were to use this tip type tool and want to cut with the end of this radius, I need to know basically what that optimal radius that I want to cut with is, as well as the angle that it's going to be engaging on the surface. And that's basically primarily where you're going to get this information from. However, when you're in PowerMill or actually writing a program for it, these angles can change. Sometimes you need to use the opposite of the angle. We'll check that out once we get into PowerMill here in a moment. I'm just going to jump over to the ISCAR website. I liked the ISCAR tools. I do like the insert tip tools, especially if I'm doing larger molds, larger tools, larger parts, because I do have tool wear. It becomes a thing depending on RPM based on the diameter that you're cutting at. And I did like the fact that I can alter and pull the inserts when necessary over larger surfaces. Amugi as well has information on their cutters for a full line brand. I do use Machining Cloud for this, and I like to pull from the Machining Cloud for most of my data. A lot of the macros that we're developing at NextGen Cam actually work real well, and we'll see our creation macro for this type of tool, as well as the holders and maybe even any shank segments for it. We do have a macro that kind of pulls that information out of the solid that's downloadable from Machining Cloud, and we're working with Machining Cloud on improving this so that we can cover just about every tool and every cutter brand that's on Machining Cloud. So easy to come in and select, create full tool lists, things like that. We'll have a webinar on that in the future as soon as that's fully developed. So please look for that. We're going to have that available fairly quickly. I'm hoping within the year here that that'll be completely done. For now, I have kind of a demo of it. Demo version of it that works with specific tools, and one of them being the circle segment tools from Amugi here. Let's jump over into PowerMill real quick. So for the demonstration today, I kind of picked this part out of all the demo parts that we have available from Autodesk here, mostly because it represents kind of the aerospace side of things, but the technology is going to be the same as we look at it and we go into some toolpaths. Now, I said earlier that we will cover some of the toolpaths. I can't cover everything on the standpoint of what best toolpaths work with this technology, just due to time. However, I will kind of jump back over to the list just so we can kind of go through supported cutting tools. So Constant Z can be used quite frequently with this, and Swarf are kind of the two parent tool paths that I used in the past for these types of tools. Along with raster, I use raster quite a bit. Where things fail, I kind of tend to jump over to raster to see whether or not I could just adjust the tool angle and see if I tool axis and see if I can't actually get a result for what I'm trying to cut. So once we get into our toolpaths here for today, I'll kind of go through each one of these, including raster, including Swarf. Starting out with Swarf, then we'll go into raster and Constant Z as we go through the toolpaths, and just kind of show right out of the get-go what you're looking at when you start using these toolpaths, and what's going to fail and what's going to succeed, basically, because there's a lot to this part and many different angles, many different undercut regions that we're going to try to get to. Let's go back to our cutters real quick. Now, I downloaded solid data from those websites and from the Machining Cloud so that I can import that data in here into PowerMill. And we're going to kind of look how we can set up these tools based on that data. Now, typically, and what's kind of become an industry standard is to download those solid files from your cutter vendor. Now, let me go ahead and pull up my Explorer window here with a couple of these files here. I'm going to go ahead and start out with one of these circle segment tools that I have here and import the solid. And I do like to start with a fresh version of PowerMill when I'm creating these tools. That way I have nothing else on the screen for two reasons. I'm going to be interrogating the data that I extract out of the profile of these cutters. There's a surface in there that didn't come in very well, but that's okay. It's not going to it's not going to do any harm to us. Now, when we bring the data in, if you're doing this in a more manual fashion to create these tools in PowerMill, I do recommend moving the tool and translating it to the world coordinate position from where it is at the end of the tool to the tip. Most of the time they come in back here on the shank of our tool. If I come over here to my colors, I am going to show sometimes they come in and the tip is separated adequately, and sometimes they don't. It just depends on the vendor and the solid model that imports into PowerMill. But let's go ahead and create a quick work plane here just so we can translate this and move this out of the way. I'll just select that bottom surface since I have a flat, and you can select it by cylinder too, and create my work plane from there. I'm going to activate that work plane. And then I'll just right click on the model, edit, and we're going to transform the entire model. And we're going to do that to the world coordinate system. It's going to translate even the damaged surface there. We don't have to worry about that. It's not going to cause any problems here. So I'll delete that work plane just to get it out of the way. Keeping things clean helped me out with kind of defining these tools in PowerMill. And what I want to do is I want to get the segment of that tool. Now, there's two schools of thought here. One is that you have that side profile along that tool. My experience is that occasionally these segments of these profiles can be broken up and can cause problems. So when I look at my front view in PowerMill from my zero origin position, I kind of want to have a full surface there to split this by, utilizing some of the tools that PowerMill needs to extract that data. What we're going to do is we're going to create a pattern here, just like we would with creating a tool holder. It's the same kind of process. We're going to go into our curve editor, and I'm going to go ahead and use the spun profile for this. And we'll go ahead and leave that in the Z-axis orientation along the Y plane, and then we'll create that profile. So I'm going to close that out, go to my front view here. You can see I kind of have my tool profile with my different sections here. Now, when we're creating this, we're focusing on two different areas here when we create these tools. That's going to be our tip segment here as well as our shank segment. So typically what I'll end up doing is I need to separate these two segments out. So I'm going to go ahead and use my segment cut tool here on this pattern. And I'll click on that segment cut tool. And what I want to do is separate the shank more than anything here. I'm going to pull the cutting data in a different fashion here. We'll do it two different ways. We'll do the form tool, which is going to use this cutting data here for the spun profile. And we're also going to do the barrel tipped tool with this cutter. Once I have those segments separated here, we can go in and start creating our tool. I'm going to go ahead and go to the home screen, and just to show everyone in the drop down of the tool creation panel, we're going to be kind of looking here at either using this as a barrel tool or a form tool. Now, each one of these tools have their benefits. Form tools are a little more lenient with the geometry of the tool itself. I have come across a few of these form tools in the past that the geometry fails on a barrel cutter, and we're going to go through the barrel cutter failure here in a moment and what we're looking at. But if you can get away with creating these tools as a barrel tool, it is the recommended type of tool to use here, mostly because barrel tools will help with undercuts and seeing undercuts without going into 5-axis. If you need to stay 3D, you can, and you can use a barrel tool for that. So let's go ahead and click on the barrel tool and create one here. Now, what we're looking at are the individual components broken down for the tip segment of the tool, and all this information can be gathered off of the websites. Now, PowerMill gives us a little bit of a better way of making these, but all this information comes directly from each vendor, and each tool that we select, such as this Imugi tip tool here, we can get that information out of the vendor here. And we're looking at all the different information here, such as the cutting diameter, and then most importantly, what they call the gorge diameter, which is going to be the barrel diameter for the most part, that radius that we're looking for. This information can come in different ways from different vendors. All right, so this is where PowerMill gives us a few tools that I like to use for this. So I'm going to pull that back up real quick, grab that diameter since I forgot what it is, and I can just cut and paste that from here. So I'm going to grab that cutter diameter there. Let's make sure I got the 1250, the 12050A there for the cutter. 472.4. When I start doing this, PowerMill's not going to give me a preview right away. Okay, there's several things here that are causing the preview to fail, and as I go through and start entering data into these, you won't always get a preview, but the status bar here will tell us whether or not that tool is going to be able to be created. Now, in order to meet this criteria, there are a few things that absolutely have to happen. You have to have the diameter, the barrel radius, the length, and this Y offset of where the barrel radius location is. Right? And this is the most important one here. If this does not basically fall in line below the length of the cutter, then a barrel cutter will fail. And usually it's the more point type, spherical type tools that fail on this creation. So let's go ahead and just get the rest of this data. Now versus going back and forth to the PDF or the information from the website, I'm just going to grab this information by using some of our direct input fields here. So I'm going to click on my lower radius, and this puts us into our measuring tools options here into PowerMill, and it sticks us right into radius. Now, with that profile created, I can just come in and grab that radius information. That's going to come directly off of the tool. Now, you want to cross-reference this information to create the tool as closely as possible for the cutting data. That way, you're not creating something that's just outside of what the tool is supposed to be defined by. As well as the barrel radius here, I'm going to grab that barrel radius. Now, oftentimes, if there's not a radius here, sometimes these will come in segmented sections. You may actually have to adjust the profile and create arcs in place to be able to get these radii here. So just keep that in mind whenever you're selecting your cutter, whenever you revolve that profile or extract that profile in some way. There may be instances where this might just fail. Now in this case, I've got my barrel radius here, so I'll go ahead and click on that. Now I don't have a top radius for this cutter, so I'm going to zero out that upper radius, and that's okay. It will resolve as soon as we give it that full tip length here. So I'm going to go ahead and come to my length option here and click on that. Now I'm going to lock this down with a projection so that I'm only measuring in Z, and I'm going to go ahead and grab that length here at that key point down to my origin point. That should bring in the length. Now the Y offset's a little bit more tricky. If the center is not defined on this cutter, we do need to find that out. So I do need to come into the pattern itself and come in and edit the pattern. And let's go ahead and create a 3-point arc here so that we can get the center point radius of where that barrel is located. I'm going to turn my instrumentation on so I can see the points that this curve's made out of. And once I have those points up, I can come in and just start snapping to my key points on the radius and then grab a tangent point so that I can get the actual barrel radius. Now you'll see there we have our point that's selected. Once that point's there, I'll come back into my tool just by accepting my pattern change there. Now we can get that Y offset based off that center point all the way to the cutter tip. Let's go ahead and grab that direct input data. We'll lock it down in Z once again. I'm going to hover over the center till I get my input cursor and come into my endpoint there. I have my my range here a little bit tight for my tolerance there. Now, once we have that resolved, and this number is smaller than that upper length, you'll get the preview profile of the tool and you'll get a successful tip for your tool. All right, so this would be a successful barrel cutter, and it is a flat bottom cutter. If this does come to a point with a point radius, you untick that, you'll get a radius option with that. So different ways we could do that. Now, if this fails for any reason, like let's say you add that data, and for whatever reason, there's an angle to the tool, maybe it's a little bit steeper, that shifts that center point up above the length of the cutter, all right, that is when it's going to fail. So if I come in here and tell this that there's 0.6 on that, say, center line diameter, then that radius actually can't be created due to the length of the cut of the part. Now, that's not to say that a cutter can't be ground that way. However, the math doesn't work out for the barrel cutter itself, and then this type of tool will fail. In that instance, whenever that happens, I'm just going to reset this so I can finish this out here. You will have to use a form tool in that instance to get this type of cutter to work. And again, we want to cross-reference these numbers to the data just to be sure that we're getting the right thing. I'm going to save some time, and I'm not going to go ahead and do that. I'm going to go ahead and just jump over to my shank so we can define the shank profile of our cutter. Now, I separated the pattern angle here on purpose. I'm going to go ahead and right-click on the highlighted section of my segment from my my shank there. And then I'm just going to right click on the pattern, edit it, and copy selected pattern only. That gives me a second pattern here that's just the shank portion that I can actually successfully revolve to and get the accurate shank defined by the cutter vendor. That can be important later on as we may be reaching down inside of a cut and we need to have that extended and shank reliefed area for clearance on our tool. So again, that's an important part to think about when we get into looking at toolpaths. I'll start to show where I'm looking at the successful type of cutter I might try to choose here, as well as reach, rigidity, all that stuff comes in play. So a little bit of thought has to go into this when you're planning on using these for programming, a lot more so than if you were using a standard ball nose end mill. However, some of the benefits that you get out of it for finishes far outweigh the time that you may have to take on that, especially if you're doing a production or you're doing a long cycle time on a tool. You'll save that in the long run. So I'm going to go ahead and close that tool. Once I have that tool created, though, it's easy enough to come in. I usually rename that tool with the name. So I'll copy the model name here, paste that into the tool, get rid of any decimal places out of it, just because that's a habit. Sometimes they fail. Once I have that named, and you can name it by vendor, you can always just save that and add that to your database any way you like. Now, I already have these cutters defined in there, so I'll go ahead and cancel that out. Once I've got that saved in there, I usually end up just resetting my forms and deleting all so that I can have a clean slate to create the next cutter. Okay, so let's jump over to our next type of tool. So on a failure, or if we need to create a tool as a form tool, we do actually have a macro to do it. The process is very much the same. I'll just import another tool here just so we can review that. I'll just drag this tipped tool in there. It's a little bit more of a different type of spherical type tool. Let's go ahead and fit screen here. Turn on our solid. So this has multiple shank regions, and this one is actually defined by color from the vendor, which can help out a lot within macros when we create the kind of slice profile from this. We can actually separate using these different colors here, which makes things a lot easier from the vendor. So we do have that going for us. Now, the way we would make this manually is very much the same. I would come in and I would create a form tool for this. Then I would come through and I would use a pattern that we've spun from the slice profile of the tool itself from the solid. Now, I'm going to go ahead and delete that tool, and let's go ahead and just take a look at our macros here for this. So we have a macro that does this for us, and we don't have to actually translate or move anything around. It's just simple enough for us to have the solid in a PowerMill session and just click on our form tools option here. It's going to go through a couple of questions here, and the options drop down here ask what we're going to be doing. Now, we do have the ability to create entire assemblies of tools with this macro, which means we can do the tip, shank, holder, and then adjust the out of holder distance for it as well. But this is just going to be the tip and shank option. And again, once we get this hammered out a little more with the entirety of the machining cloud data, we'll have a full preview on that, either in a video form or even in a webinar form. But I'm going to use the tip and the shank because I want to extract both of those out of this data. I'll select the model. It's going to go through, do the slicing of the profile, and it's going to ask me, well, what do I want to do with that? Do I want to create a form tool? Yes, I do. Grabs both ends of that data and creates the tool for me. And just like that, without having to go through all the labor of creating the profiles myself, I've got a successful form tool out of this. So different ways that we can create those tools. Again, whether or not they succeed based on cutter creation and what you're using them for depends on the geometry of the tool. I actually would go in and make two separate ones of these. I have form tool as well as barrel tool cutter with it. If I'm lazy and I want to get through it quickly, or it's just more direct 3D, I'll just create the form tool because it's fast for me to use the macro. If I need to undercut in any situation, I usually go in or use constant Z, not optimized constant Z for the toolpath. Then I will create it as a barrel tool. I'm going to jump over to PowerMill real quick. And again, if you guys have questions, please put them in the question field at the end of the demonstration session here. I'll go over any questions with anybody, and we can kind of have a open chat if you want to. I can unmute anybody in the session here that has questions. So with types of toolpaths and types of cutters, I am using that Imugi cutter for this demonstration that we created. I added a holder to it, one of the rigid holders that I like to use to get in and get into reach on the machine tools, give me the distance that I need for the length that I need tilt angle that I might be using. Let's first take a look at a swarf toolpath. All right, now I have a couple of toolpaths already created to save some calculation time here, and I'm just going to go into settings. Now swarf, as we all know who use swarf, basically uses the tangent contact point of the tool. Now, within my settings, we're going to be looking at tool axis primarily for controlling the angle of engagement of these cutters. And with Swarf, automatic kind of takes care of some of that for us. All right. Now, this tool is set to automatic, just calculated using the selection of the surfaces like we would with Swarf. If I come in and actually simulate this toolpath from here, you'll notice that it does an okay job of finding that angle of engagement, but it's finding it at the upper tangency of our radius. All right, now this would actually do a pretty decent job of creating this surface up until the point where it gets to the bottom where it tries to blend to the radius. We're actually not going to get the result down here that we're looking for towards the end of the toolpath. So if I come down here towards the end, we're going to actually see that, and if I can get it to select the toolpath, there we go. You know, we're still quite a ways down on that. Even when we get to the bottom of the toolpath here, you know, we're not actually going to be able to blend that radius at that contact angle because of the backside of our tool. Now, again, choosing your selection of your tool is going to depend on rigidity, reach, things like that. This actually did a pretty decent job of getting down below there as it travels up. I have just enough angle and just enough clearance to get away with this. I have a little bit of shank contact that it might disturb me, and it really depends on how much clearance you want from your shank there. A lot of times in these operations, you have to verify that closely because you're going to need to be pretty close to your shank, and this can be a pucker situation for any of your operators. This type of stuff I really like to show the operator to make sure that they're comfortable with it while it's going to run. Or if I'm running it, I'm usually verified this to the nines so that I know that I don't have any issues colliding with my shank or my holder. But let's go ahead and take a look at what we can do to change this tool axis a little bit. Now, all of the data that we get from vendors can either come based off of the flat of the tool from that tool angle, or it can come from the tool axis itself, meaning along the actual shank of the tool, so whatever direction that we're cutting with. Prepping for the tool path before I jump into that, I usually always create a work plane pretty close to my main plane that I'm trying to reach down into the geometry. This can help you on the onset so that you don't have any issues reaching down into cavities like this. All right, so if you create your work plane for your tool path so that your machine can successfully tilt to the work first, and if I look at the top on this, I'm kind of averaging out the angle from that wall so that the majority of my undercut tilt is just on one side. All right, now that takes a little bit of playing with the initial work plane setup to figure out what type of clearance that you may need or have. Now you can do a couple of things for this. You can utilize, of course, our undercut tool here that kind of indicates where the undercut section is. You can also, and I'll copy the work plane for this, activate that work plane. Let's go into work plane editor. You can also then come into the work plane editor and you can utilize any of the twist around options here to kind of give you a little more clearance to try to find the average so that you can reach the majority of material here. So I'm going to twist around Y for this, but as I update that twist, you see my image updates for my clearance for my undercut. I'm going to cancel out of that. And I'll activate my previous work plane for this. Let's go back to our regular blue shaded view here, just of the contrast of our tool path. And let's come back into our tool axis. So again, with this, right off of the rip of the calculation here, it could successfully machine the majority of the features on this part. However, what I want to actually be able to do is alter the tool axis and force the lean based on the average. And again, with Swarf, it only gives us one option. It's not allowing us to actually control the contact point of the tool to the surface. like we would typically see with all the other toolpaths. All the 3D toolpaths allow us to kind of contact with the tip of the tool based on either contact, normal, or vertical, or a few other options depending on the toolpath. But in this case, it was always forcing the along of this tool along the shank. Now, I did go to the website and figure out the angle that I would like. Now, their optimal angle is up at about 12 degrees. I find that with this tool, I want to find the angle that I want to use here. I did actually figure that out as 8. Now, figuring this out, if I jump back over to my other session of PowerMill, and we just look at that pattern profile real quick, and I'm going to have to spun a profile from this tool real fast. And I'll just use the geometry. I'm not going to have to place it in place or anything like that. What we're looking for is the contact that we're going to be on our surface. It's not always straightforward. A lot of times what you'll get as the contact is the average angle right at the center of the cut. If we're reaching down inside to a deep pocket, we may actually end up being more towards the end of the tip of our spherical tool when we do this. I find it handy to just come in and create my own pattern here anyway, depending, or we can pull the data off of the website, pull in a DXF file, whatever the case might be. But to come in here and just really get this done real quick, let's just spin profile this. And what I want to do is I want to just create a line and attach that line to the tangency of the cutter, right? So if I just create a single line and I come in and attach that tool. Now, if this is a cutter that is made up of segments that maybe this is a line itself, I may not be able to get that angle from that tangency. But whenever you grab a tangency and you create a line of a sphere, usually the angle will show up as well. And we can actually get that distance off the angle. You can snap a line to kind of gauge what that angle is, and then of course measure that line to get that data. And that's how I kind of can get where maybe I want to contact on that type of tool, what that successful angle is I'm just going to measure the angle of the line that I created tangency to the cut itself. I'm going to cancel out of that, jump back into PowerMill. I know that from the data that I extracted earlier before the presentation that I want to kind of put 8 degrees in there, and then I'll go ahead and calculate that 8 degrees. Of course, I do need to select my surfaces. That does help. That's a habit that I have always had using PowerMill, always forgetting to select my surfaces here. So it'll calculate and manage that swarf calculation for us. Now, we do have a tool that we like to use, a macro that does this for us. And if I go ahead and just reset this to automatic, and I'll recalculate the toolpath. What our macro does is, based off of the criteria for the type of toolpath that you're using, it decides the direction of your work plane to your work, and then extracts that angle information by itself to give you the successful toolpath angle, as well as the successful step down based off of the scallop height you're looking to create the surface finish. All right, I'm going to pull the macro up for you just so you can see some of the technology here. So that's our Barrel Tools macro here. Autodesk has had this for quite a while. We have improved on it quite a bit. We actually added raster capability to it. And we're looking at kind of improving some of these things in the future from these old macros. This macro has been around for a decade, if not more. I don't know how long this macro has been around, but it's been out there for quite a while. Again, we can make these macros available to our users. But you can see here that this macro string is letting us know that these are the successful toolpaths that we can use with this, one of them being Swarf. And if I jump back into PowerMill, I'll go ahead and go to my Demos tab here. I've actually set this up so that I can optimize it based off the selection there. So if I click on that Optimize Barrel tool, it's going to pull up another window, and it's basically asking me, well, what's my desired tool tip for this tool path? I'm going to go 8 degrees for that. Then it's going to ask me what my maximum scallop cusp height is for this. Now, the integer that pulls up is in metric, but it does take inch as well. So let's go ahead and say 4 millionths on that. Because it is a Swarf type toolpath, there is some technology in there that's asking me, well, what would I like to do for that scallop height? In this case, we have all of our offset settings for it, which it's going to automatically set within the toolpath. So I'm going to offset up from this. Offset up allows us to basically see the edges and shorten the toolpath based on the cut versus offset down, which might extend things, or even merge, which is going to merge the toolpath together and taper my cut. So I'll offset up for this. That's going to find that optimal angle. Now, because I have it set to automatic, it actually didn't jump to lead lean on its own, but if I open lead lean here, I do get that angle calculation. Now versus 8 degrees from it, it did the opposite angle based off of where the work plane was so that it can clock the tool accordingly to the actual tool axis. All right, now otherwise this is something that we would have to do on our own. You usually end up pulling a calculator up and going 90 degrees, minus whatever the 8-degree tool angle is to get that 82 degrees. Now, depending on the side of the cut, you may or may not get that negative 82. You might start and try positive, and then your toolpath is going to fail, or you're going to get a bad result. It's very easy to come in, edit this, just do the opposite of the angle that you've selected, and it will correct itself. All right, so with that calculation set there, I'll just calculate that once again. Oops. And actually, it did the opposite on that one, sorry. To get that 8 degrees. And we're going to try that on a couple of other things here. I might actually have to look at the macro and make sure I did that right for that for the swerve calculation. Usually I just pull the data myself on that one. Let's go ahead and take a look at just kind of another option here. So just to demonstrate the reach of your tool, you might select a barrel tool that is more conically tapered to maybe speed up RPMs or whatever the case might be. But you do have to keep in mind that once you're getting down in certain regions, such as the radius, or even down here in the lower radius of the tool, that tool's reach is going to gauge whether or not you're going to safely clear on that tool or not. So we're definitely gouging in that position. So that's just kind of an example of either not enough angle on it, where I would have to increase the angle in order to clear a little bit more and clear the holder for the reach and get further up the tip. Now, the reason why I wanted to show this is because as we increase up that region of that tip, your feeds and speeds are going to come into play depending on your material. I just want everybody to keep that in mind. When I've cut with this, the times that I've used these tools on titanium and aluminum, there is differences in both the scallop height capability that's calculated, as well as the RPMs that we use, just based off of the diameter and where we're cutting on the tool. But that is kind of an example. I'd like to just keep that in mind at that place. For the next example we've got here, let's go ahead and take a look at this sidewall here. So I've calculated this tool path with a raster pattern. And if I simulate the tool, this is coming down vertically from it. Now my vertical step over, I have a contact point that's just right around the tip of the tool, like similar with a ball nose end. Now I'm going to go ahead and open the settings on that tool path. Recycle the tool. There are some edits involved in here. Now, with that calculation, I will point out that whenever we're cutting, and this is an aluminum part, so I did want to go both ways with this, we're always going to want to keep our ordering to one way when we initially calculate this toolpath in PowerMill. And this is kind of a rule that I kind of teach whenever we teach 5-axis, is that your tool axis angle definition is set to a specific angle at this point, and based off the contact normal of the surface, right? So if I say 0 to this contact normal and I calculate this toolpath, this might take 1 second. You'll see the contact normal of the surface is actually directly at the angle. Contact normal means always straight within line of the point of the tool. All right. So when we're thinking about that contact angle of that surface, that's where we're coming in and adjusting that lead lean. Sorry about that. I got distracted. Now, there's always going to be some things that we need to repair in the surfaces, but when we're leaning and leading, and if I simulate this tool, and just simulate it from the start. If we start leaning to one direction, then that tool is going to tilt over that direction based off that lead lean. Well, once we turn around with our toolpath to go the opposite direction, then what happens is it'll lean the opposite direction. So we end up leaning either positive or negative on that tool axis angle to the surface. Let me go ahead and recycle this. Let's put in 75 degrees in there. Calculate that tool. So from 90, calculating one direction or the other. And it's applying my edits to the toolpath from the previous toolpath. And there's that opposite angle. That's the undesired angle that I might want at that point. It's also wrapping around the top of the surface. But after calculating that based off of a one-way, in order to get it to move back and forth, we just simply go into a toolpath edit, and then we would, of course, use our alternate directions to flip that to be a zigzag toolpath on that surface. Now, this is another calculation that was from vertical here that doesn't have any adjustment to it. If I go into those settings, this one should just be contact normal. If I come into that tool axis there, actually this one has 82 degrees set up to it. Let's go ahead and do the raster toolpath for this one. Or I mean the constant Z toolpath for this one. So I rastered that one, and based off of my raster, I also set my work plane along that surface, and I also clocked the X and the Y pointing in the direction of the surface so that I can get the raster angle correctly to it as I calculated these toolpaths, right, for that angle. Now, if I run my segment tool here, I can get that radius of the tool. I do believe this one is remember that that radius diameter. Then we'll go into the tooltip angle, and for this tool, I believe it's like 20 degrees, somewhere around there. Up specified. I'm getting that opposite kind of thing there. So if it's failing on that calculation, that means my angle is actually pointed in the wrong direction. I've given it the wrong data here for that tool axis. So I would need to alternate that data in order to get a successful toolpath out of this. Now we have more successful toolpath. Now you'll notice there's a lot of chaff in this toolpath. There's a lot going on here, things that I'm not going to want from the calculation. Now that's just the raster toolpath finding segments where it's basically reordering the toolpath as it saw fit, and then it's also wrapping just outside of my boundary area. So sometimes when you're using, especially raster toolpath, you're going to get some things that you don't want from the toolpath itself. That's where I'll go ahead and trim my toolpath or trim anything out so that I can get rid of it with a limit and just come in a limit and maybe a limit to the boundary that I have active. I'm going to keep the inside of that boundary. And this will just kind of clean up anything outside of that toolpath and help clean it up just a little bit. Now I've got leads and links here, and you can see this is going one direction at this point, so it's kind of just looping around on that toolpath itself. So in order to get rid of those loops again and make it back and forth, that's where I'd come in, zigzag it, and there would be reordering involved here. It's not always going to be as clean as we'd like it to be, but eventually with the edit toolpaths, you can get to the very clean toolpath where you have back and forth method working out that distance. Now, I'm going to go ahead and go to that constant Z here. This one is, again, calculated vertically. I'm going to turn off my leads and links for the example here and just take a look at it, simulate it, just so you can see it's cutting kind of directly with the radius there, vertically from the active work plane. Now, I set that work plane along that surface on the bottom here just to give me a different angle projection to it. But if we look at that, you can see that that contact point's set there. I'm going to go ahead and run my macro for this. And it's going to ask for my desired angle tooltip. In this case, I'm going to say 8 degrees that I pulled from the information from either the website or the tool measurement. Hit OK to this. We're going to give it the desired scallop finish height. And it's going to reset the tool angle and then also change the step down for us. Now my boundary didn't come out really clean there, but that's okay. It's going to ignore that segment. Now you'll see that difference in that step over is quite dramatic. And if we go into that settings by using that scallop height, also changing that tool tip angle, it set my constant Z settings down here to almost 1/8 of an inch. Now that could be the correct contact for that. However, I've also found that depending on the calculation, I usually like to err on the side of caution as far as where I'm at on that tooltip. So I'm going to check the tool axis first. You can see it added the minus 82 degrees there. Let's go ahead and just simulate that real quick from one of these points. I'll grab one of these middle toolpath points there and simulate to it. You can see it altered that contact angle for me. And again, it's similar to the Swarf toolpath. It found the center of that angle, right? So I may need to increase that angle just a little bit. When I increase that angle, that step over distance is going to change. Now this doesn't look too bad as far as the scallop height goes, but I usually end up taking that scallop height and maybe halving it at that point. And even still, if I half that, and it just depends on material and the cut, I err on the side of caution just because I like to get that surface finish right. I'm still moving 63 thousandths or a 16th of an inch versus maybe 5 or 10 thousandths on that step down or step over on the toolpath. So I'm still getting a lot of efficiency out of it. Again, it's just going to depend on where you're cutting on that cutter. But that macro did successfully set that tool axis for me, and I can actually calculate this with a little bit smaller step over. And maybe that's a toolpath that I would want to run. I'm going to turn on the leads and links real quick. You can see that's a one direction toolpath once again. So I'll go up and do my trick where I come into my reorder. Let's go ahead and reorder and reverse those. Now I have more of a back and forth. Now again, the order of this, a little bit out of sync. I'm going to have to take and move some of these toolpaths around to get them in the order that I want, so that it comes down the top here, then comes down one side and then the other. But you can kind of see what the idea is here with these conical spherical tip type barrel tools, where we actually want to increase that step over, gain that efficiency out of it. Now, before I let you guys go and we go into QA, let's go ahead and come into one of these floor segment operations. I just have one of those lens tools. I pulled this one off the Friesa website just to kind of show with, again, raster, one of my go-to toolpaths for most of these types of toolpaths that I create. Mostly because I can alter that direction. A lot of times, surface data is not going to be adequate to control a toolpath. So I didn't choose like a surface finish toolpath for this, mostly because from this angle and the angle of engagement, a surface finish is going to run along the inside directions, the UV directions of the surfaces. And a lot of times this can be like a patch surface where it's a grid. And that all depends. And I have occasionally had to edit surfaces within PowerShape or PowerMill Modeler to get successful toolpaths. So it's never going to be kind of straightforward, but I'm just going to simulate this at this point. And with that simulation, I think that I'm at my hour and I'm going to have to open it up for questions. So I'll go ahead and open the questions field. A couple of questions here regarding sending the data and the information. Yes, I most certainly can. To everybody who's got that question in there, we'll send all that to you. With this setup and these settings, I did come from a vertical position here for the toolpath, just to go in the tool axis settings here at lead link of 28 degrees. Now this was something that worked out direct, and it's important to note that that contact normal to the surface is what I'm looking for. We typically don't want to do a vertical in this situation for our tool axis, mostly because you're tilting the angle of the sphere of the tool from the surface itself. We just need to determine whether or not that's actually coming directly from the angle of the tip of the tool, or along that shank.